Welcome to lecture number 106 of digital electronics. In this lecture, we are going to deal with shift register counters. So basically there are two types of shift register counters, which are given by the names ring counter and Johnson counter. This Johnson counter is also known as twisted ring counter. Now coming into a ring counter. Now generally what I have mentioned in the earlier lectures is that shift registers need to be designed only using D flip-flop if possible. So I am going to explain about a ring counter on the basis of D flip-flop. So here I am going to explain about 4-bit ring counters. It can be made to 3-bit or 2-bit or 5-bit or 6-bit, no problem. But here I am going to explain only 4-bit ring counter. Now for a 4-bit ring counter, you should have number of flip-flops. Number of flip-flops is equal to 4. There should be 4 flip-flops. Now coming into ring counters, number of flip-flops is equal to 4. So you need 4 D flip-flops. Now as a ring counter, what is the specialty in that? Initial state can be 0000. Initial state is 0000. Now initially the last element will be made to 1, 0001, and this 1 is getting rotated. So I am going to drawing the state diagram. First. Now 0001, then comes what? Then it comes, there is a mistake over there. Initially you are loading 1 to the first bit, that is 1 0 0 0, that is the MSB. Then in the next clockwise it will be changed, like 1 will be changed to next bit, so it will be 0 1 0 0. Again what happens? This 1 will be changed to next bit, so it will be 0 0 1 0. Again it will be changed to next bit, that is 0 0 0 1, and it will remain there. That means 0 0 0 1. Again this one will be made to the leftovermost position, and this ring continues. So this is the basic state diagram of a ring counter. So this is also known as, the valid states are 8, this is 4, this is 2, and this is 1. So this ring counter is also known as 8421 counter if it is a 4-bit counter. Whereas if it is a 3-bit, it becomes 421 counter. If it is a 3-bit counter, it comes to 421 counter. That means 100 is not there. We can start from 100 0 1 0 0 1, then come back to 100. It will go like that. Now coming into the design of that. First of all, I need to draw the present state, next state table. Along with excitation table of of D flip-flop. So drawing the figure, we are having present state, next state. So here what we are going to deal with, we will deal with only the valid states for the time being. We will deal with only the valid states. That means this is an invalid state, so we will deal with 8421 only for the time being. So what happens? Q4, Q3, Q2, Q1, Q4, Q3, Q2, Q1. So what do you have? 1 0 0 0, that is the present state, it will be changed to 0, 1, 0, 0. Then comes 0, 1, 0, 0. Then it will be changed to 0, 0, 0, 1. Sorry, 0, 0, 1, 0. That is 0, 0, 1, 0. Then comes next state is if it is 0, 0, 1, 0, it will goes to 0, 0, 0, 1. And if it is 0, 0, 0, 1, it will go back to 1, 0, 0, 0. Okay. Now let me write D4, D3, D2, D1. What is D4? D4 is equal to next state Q4. So we can write 0, 0, 0, 1. What is D3? D3 is equal to next state Q3. That is 1, 0, 0, 0. That is D3. Now coming into D2. Now coming into D2. What is D2? D2 is next state Q2. That is 0, 1, 0, 0. Now what is D1? D1 will be next state Q1. That is 0, 0, 1, 0. 0, 0, 1, 0. Now you need to write D4, D3, D2 and D1 as a function of present state Q4, Q3, Q2, Q1. That is how we have designed the counters. Now if you are looking to D4, we can see if you are looking to the present state Q1 and D4, present state Q1 column and D4, we can see that both columns are same. Therefore we can write D4 is equal to Q1. Similarly, if you are looking into present state Q2, and next state present state Q2 and D1, present state Q2 and D1, present state Q2 and D1. We can see that the expressions are same. So we can write what? D1 is equal to Q2. Now if it is 0, 1, 0, that means next is if you are looking like this, if you are looking like present state Q3, 0 and D2, 0 and D2 and D2 column, we can see that these that two columns are exactly the same. Therefore we can write D2 is equal to Q3. Therefore we can write D2 is equal to Q3. Now coming to the last one. Now if it is 1, 0, 0, we can what we can see. We can see that Q4 column is exactly same as that of D3 column. Q4 column is exactly same as that of D3 column. Therefore we can write D3 is equal to Q4. D3 is equal to Q4. Now if you are writing the expressions for D4, D1, D2, D3, how if you are drawing the logic circuit, initially what should be drawn? You should draw D4. Okay, you should draw D4. So you are having D4. D4 is here. Q4 bar. Then what you have is D3, Q3 bar. Then comes D2, that is Q2 bar. Then comes D1 with Q1 and Q1 bar, and the clock is kept common. You can have a common clock. Clock is kept common. Okay. Now what is D4? D4 is we can start from D4. D4 is equal to Q1. D4 is equal to Q1. So you can shorten that way. D4 is equal to Q1. Now what is D3? D3 is equal to Q4. D3 is equal to Q4. So you can short that. Then what is D2? D2 is equal to Q3. D2 is equal to Q3. Therefore, we can show that. Now, what is D1? D1 is equal to Q2. D1 is equal to Q2 means you can show that. So, what happens? This is basically a ring counter. That means the output of the last flip-flop, this is flip-flop number 4, flip-flop number 3, flip-flop number 2, and flip-flop number 1. The output of the last flip-flop is fed back to the first one. So, here the valid states are 8, 4, 2, and 1. Now, if you are drawing the timing diagram, okay, of this flip-flop, you will get like this. So, I am having a positive edge string 1, 2, 3, 4, 5, like that. So, 1, 2, 3, 4, 5. So, I am drawing the timing diagram. Okay. This is the clock pulse. Okay. So, what will be Q1? Okay. If you are looking to Q1, what is Q1? 0, 0, 0, 1, right? Yeah. Okay. Q1 is, if you are drawing Q1, Q1 is, this is 0, 0, 0, 1. So, this is Q1. Now, what is Q2? Q2 becomes 0, 0, 1, 0. So, we will get start from here 0, 0, 1, 0. Like that it will go. Now, what is Q3? 0, 0, 0, 1, 0, 0. What is Q4? Q4 becomes 0, 1, all others are 0. So, this is the basic timing diagram of, so this is 0, this is 1, 0, 1, 0, 1, 0, 1. So, you can draw the timing diagram of this ring counter like this. That means for each clock you are getting different states. Okay, that means Q1 will be 0, 0, 0, 1, Q2 will be, Q2 is very like that, and Q3 is very like 0, 1, 0, 0, and Q4 is very like 1, 0, 0. Okay, so that is the basic timing diagram. Okay. So, that is regarding a ring counter. So, the specialty of ring counter is that the output of the last one of the last flip-flop is fed back as input of the first flip-flop. Similarly, if you are having only 3 inputs or 3 flip-flops, what happens? The Q1 will be fed back to D3. If you are having only 2 flip-flops, what happens? Q1 will be fed back to D2. Whereas this flip-flop number 4 and flip-flop number 3 will not be there. That is the only difference. Now, coming into twisted ring counter. Twisted ring counter or Johnson counter. Okay. Twisted ring counter or Johnson counter. Twisted ring counter or Johnson counter. Now, here, what happens is that, now coming to the various states of that. Okay, let me go with the 4-bit twisted ring counter. Okay, and that means you need 4 flip-flops. So, 4, which is D flip-flop. Now, let me show the sequence of that. Initially, it will start from 0, 0, 0, 1. Because you are having 4 flip-flops, you can use 4 bits. Then comes, it will be initially it will be 0, 0, 0, 0. You can start from 0, 0, that means 0. Then what happens? 1 comes in the first bit. So, it is 1, 0, 0, 0. Then what happens is that, next is 1 will be transferred to here, but this 1 will remain there. That is 1, 1, 0, 0. Then comes what? 1, 1, 1, 0. That means this one will transfer to here and that one will remain here. Then comes 1, 1, 1, 1. Okay. So you will get 1, 1, 1, 1. Now all bits are 1. Now again what happens is that now 0 will come in. So 0, 1, 1. It will go as 0, 1, 1, 1. Then comes 0, 0, 1, 1. then comes 0, 0, 0, 1. At last it goes to 0, 0, 0, 0. So the value states are 0, 1, 0, 0 is 8, 8 plus 12, 12 plus this is 14, 15, then this is 7, this is 4 plus 2, 6, sorry, this 3, this not, yeah, 2, now this is 1, okay, so 3 and 1. Basically 3 and 1. So these are the value states. So this is how it is transforming. So initially it will be 0, 0, 0, 0. Then it comes to 1 double 0. That means complementing the first bit. Now coming into, now that one will be taken as output of the second flip-flop. Then that one will be taken as a next flip-flop, provided the first flip-flop, the output is remaining as 1. So coming into the present state, next state table along with the excitation table of D flip-flop. Present state, next state table with excitation table of D flip-flop. With excitation table of D flip-flop. How did it look like? Let us check. Okay. So we are having present state Q3, Q2, Q4, Q3, Q2, Q1. Next state Q4, Q3, Q2, Q1. Next is what we are having is D4, D3, D2, D1. Of course, D4, D3, D2, D1 is equal to next state, Q4, Q3, Q2, Q1. Now, if the present state is 0, 0, 0, 0, it will go to 1, 0, 0, 0. If it is 1, 0, 0, 0, it will go to 1, 1, 0, 0. If it is 1, 1, 0, 0, it will go to 1, 1, 1, 0. If it is 1, 1, 1, 0, it will go to 1, 1, 1, 1. If it is 1, 1, 1, 1, it will go to 0, 1, 1, 1. If it is 0, 1, 1, 1, if it is 0, 1, 1, 1, it will go to 0, 0, 1, 1. If it is 0, 0, 1, 1, it will go to 0, 0, 0, 1. And if it is 0, 0, 0, 1, it will go to 1, 0, 0, 0. Sorry, it is 0, 0, 0, 0. It will go to 0, 0, 0, 0. Okay, then it will come back. Now let me write D4, that is 1, 1, 1, 1. That means D4 is equal to present state, next state Q4. That is 1, 1, 1, 1, 0, 0, 0, 0. Then D3 is equal to next state Q3, that is 0, 1, 1, 1, 1, 0, 0, 0. What is D2? D2 is next state Q2, that is 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0. What is D1? D1 is equal to next state Q1, that is 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, and 0. So you got D4, D3, D2 and D1. Now, how will you do it? That is the question. Now, if you are looking to D3 and Q4, we can get the same thing, right? If you are looking to D3 and Q4, you are looking to the columns of D3 and Q4, we are getting the same values. Therefore, we can write D3 is equal to Q4. D3 is equal to Q4. Now coming into D2, if you are looking to Q3 and D2, right? Yeah. So looking to present state Q3 and D2. Both columns are exactly the same. Therefore, we can write D2 is equal to Q3. D2 is equal to Q3. Now coming into D1. D1 means D1 I have done a mistake there in writing. Erase it. D1 is present state, is in, sorry, it is 0, 0, 0, 0, yeah, 1, 1, 1, 0, okay. Now if you are looking to D4, if you are looking to D4, I forgot that. If you are looking to D4 and Q1, yeah, if you are looking to D4 and Q1, right? Okay, if you are looking to D4 and Q1, you can see that Q1 is, or D4 is a set complement of Q1, right? So you can write D4 is equal to Q1 complement. Now what is remaining? Remaining is D1. Yeah. So remaining is D1. So if you are looking to, yeah, if you are looking to Q2, if you are looking to Q2 and D1, if you are looking to the column of Q2 and D1, you can see that it is exactly the same. So you can write D1 is equal to D1 is equal to Q2, is equal to Q2. So writing it in a particular order, you will get D1 is equal to Q2. Then what? D2 is equal to Q3. D2 is equal to Q3. Then comes D3 is equal to Q4. D3 is equal to Q4. And the last one is D4 is equal to Q1 bar. D4 is equal to Q1 bar. If you are drawing the logic circuit, of that, okay, we are having 4 flip-flops. So we will start with the D4, Q4, Q4 bar. Then comes D3, Q3, Q3 bar. Then comes D2, Q2, U2 bar. Then comes D1, Q1 bar. We have the clock. Clock is remaining there. Now what is D4? D4 is equal to Q1 bar. D4 is equal to Q1 bar. Now D3 is equal to Q4. Okay. Now what is D2? D2 is equal to Q3. Yeah. What is D1? D1 is equal to Q2. Therefore here you can see that the complemented output of the last flip-flop is fed back as input of the first flip-flop. That is why the name is known as twisted ring counter. That is known as twisted ring counter. Okay. Now coming into the timing diagram. Of twisted ring counter. Okay. So which are the valid states? Valid states are, okay, so I will draw the clock first. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the first clock pulse, second clock pulse, third, fourth, fifth, sixth clock pulse, seventh, eighth, ninth. How many states are there? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 are there. Okay. Now coming into Q4. Q4 is again is 0, 1, 1, 1. 0. So in the first clock it is 0, 0, then 1, 1, 1, 1, 1, 1, 0, 0 1 1 1 sorry, 4 1. That is 0 1 1 1 1, then 3 zeros, 1 2 3. So we can write it as 0 1 1 1 1 0 0 0. So that is regarding Q1. Now coming to Q2, what happens? Q2 is 00 4 Q3. Now coming to Q3, that is, this is just Q4, sorry, this is Q4. Now coming into Q3, how will be Q3? Q3 will be 00 4 ones, 0 0 0 0 1 1 1 1 1 1 1 1, 00 4 ones and 00 0 0. Now coming into Q2, how will be Q2? Q2 will be 4 zeros, 4 ones and 0. 1 2 3 4. Q2 will be 3 zeros. Sorry, there is a doubt. Q3 will be 3 zeros. Then comes to 1 1 1 1 1, then it goes to 0. That is 1 2 3, then 1 1 1 1 0 to go like that. Now what is Q1? 0 0 0 0 0 0, then comes 1 1 1 1, then comes 0, like that it will go. Okay, so this is the basic timing diagram of a twisted ring counter. Hope you understood how you have drawn the timing diagram. Now, next part. Now we have designed what? Now you have designed a shift register counter. Now you have designed a shift register counter, that is ring counter and Johnson counter. Now, next part is how to make a self-starting ring counter. We will explain that also in this lecture. This is self-starting ring counter. So, in the while we are discussing a ring counter, we are not discussing about self-starting. So here we will discuss about self-starting ring counter, right? Okay. 1 second. Now coming into self-starting ring counter. Self-starting ring counter. Okay. How you can make it into a self-start? That is a question. Now, see, if you are making it into self-start, so if it is a ring counter, what is the state diagram? If I am drawing the state diagram, it is basically an 8 4 2 1 counter. If it is 4-bit, it is basically an 8 4 2 1 counter. So first I would write 8. So it is 1 0 0 0 4 8 4. Then comes 2. That is 0 0 1 0 2. Then comes 1. That is 0 0 0 1. Okay. Now see, here the only valid states are 8 4 2 and 1 are the only valid states. Now how you can make it a self-starting ring counter? That is a question. That is a question which is coming in here. Okay. Now Okay. Now if they, now you can design in some ways. Okay. So which are the invalid states here? Here the invalid states are 0, 1, 2, 3, 4 is other, 5. Then comes 6, 7, 8 is there, 9 is an invalid state, 9 is an invalid state, 9, 10, 11, 12, 13. I will write in a separate way. In the case of a ring counter, the invalid states are, first of all let me write the invalid states. The invalid states are 0. 1 is there, then 2. 2 is an invalid state, 3. 3 is there, 4 is a valid state, then 5, 6, 7. Now 8 is a valid state. Now if 8 is there, then 9, 10, 11, 12, 13, 14 and 15. These are invalid states. Let me write the 4-bit combinations of that. So what do you get? 0, 0, 0, 0 is 0, 0, 0, 0. 3 is 0, 0, 1, 1. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. 9 is 1, 0, 0, 1. 10 is 1, 0, 1, 0. 11 is this one 1, 0, 1, 1. Then 12 is 1, 1, 0, 0. 13 is 13 is 1, 1, 0, 1. 14 is 1, 1, 1, 0, and 15 is 1, 1, 1, 1. Okay. Now, how you can make it self-starting? That is a big question. Okay. Now, if you are looking to 8, what is 8? 8 is 1, 0, 0, 0. Okay. And 4 is 0, 1, 0, 0. This is 0, 1. Okay. Now, see, if an invalid state comes, there is an easy way. You should make it to the first state, initial state or any valid state. Okay. There is an easy way. So here what I am going to do is, if any of these invalid states comes, it will be counted back to 8. It will be counted back to 8. That is 1, 0, 0. That is what I am going to do here. Okay. So if I am okay, that means there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 invalid states. These 12 invalid states will be mapped in the next clock. It will be mapped to 8. Okay. So let us try that. And again, that design is based on D flip-flop. Okay. So coming here. So first of all, let me draw the present state, next state table along with the excitation table of D flip-flop. So coming into the table, we are having present state, next state. We are having Q4, Q3, Q2, Q1, Q4, Q3, Q2, Q1, and D4, D3, D2, D1. So we should write all the states from 0 to 15 directly. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is 1, 1, 0, 0, 12. Now comes to 13. 13 is 1, 1, 0, 1. 14, 1, 1, 1, 0. 15. That is 1, 1, 1, 1. Okay. Now it is 0, 0, 0, 0. It should go to 8. That is 1, 0, 0, 0. So let me write the decimal equivalence of that first. So we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay. First of all, let me write all the invalid states to next state. So 1 is a valid state. So we can write it as 0, 0. It will go to 0, 0, 1, 0. 3. 2 is a valid state. If 2 is there, it will go to 4, right? That is 0, 1, 0, 0. Now 3 is an invalid state. If 3 is there, it will go to 1, 0, 0, 0. 4 is a valid state. If 4 is there, it will go to 1. 1 means 8, 4. Sorry, it will go to 2. 8, 4, 2. That is 0, 0, 1, 0. 8, 4, 2, 1. 5 is an invalid state, so it will go to 8. 1, 0, 0. 6 is an invalid state, it will go to 8. 7 is an invalid state, it will go to 8. 8, if it is 8, it will go to 4. That is 0, 1, 0, 0. 9 means it is an invalid state, it will go to 1, 0, 0, 0. 10 is an invalid state, it will go to 1, 0, 0. 11 is also an invalid state, it will go to 1, 0, 0, 0. Then 12 is an invalid state, it will go to 1, 0, 0, 0. 13 is an invalid state, it will go to 1, 0, 0, 0. 14 is an invalid state, it will go to 1, 0, 0, 0. 15 is an invalid state, so it will go to 1, 0, 0, 0. Now, if you are writing the excitation table of D, you will get that it is similar to next state Q itself. Therefore, we can write D4 as 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, that is D4. Now D3 is also exactly the same. So it is 0, 0, 0, 0, 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then comes 1. Then all others are 0. 1, 2, 3, 4, 5, 6, 7. Now comes to D2. D2 is exactly, so I will write 0, 0, 1, 0, 0, 0, 0, 0, again 0, 0. Then comes 1, 0. Yeah, then comes 0, 0, 0, 0. 0, 0, 0, 0. Then here also you will get 0, 0, 0, 0. Now all others are 0, right? So you write 1, 2, 3, 1, 2, 3, 4, 5. Now let me check the expression of D4. Okay. So to derive the expression of D4, I need a K-map. Okay. To find the expression of D4, you need a 4-variable K-map showing Q4, Q3, Q2, Q1. 1, 2, 3. 1, 2, 3. 0, 0, 0, 1, 1, 1. 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now coming into D4, it will get 1, 0, 0. 1, 0, yeah. 1, 0, 0. Now comes to 3. 3 is 1, 4 is 0. 3 is 1, 4 is 0. Then 5, 6, 7 it is 1. 5, 6, 7 it is 1. Then comes 8 is 0. All others are 1. 8 is 0. All others are 1. Okay. Now, how to find the expression for D4? That is the next question. So here you can have this is you can make a quad like this. So you get Q4, Q3. Q4, Q3 is here. Then you can make a quad like this. So this is what this is, Q2, Q1. Then another quad you can make. Whether you can make another quad here. Yeah, we can make another quad because see this one and this one needs to be included. So we can make a quad like this. Okay, including this one. So here what we get, which is common? Q4 is common. There Q1 is common. So you get Q4 Q1. Then another quad you can make like this. So what is it? Here Q4 is common. There Q2 is common. So Q4 Q2. Then another quad you can make like this. You should use these 4 quads. What is it? Here we can make it as here which is common. Q3 is common. Q3 is common, and here which is common Q3, Q2 is common, and to include this one you can go for this quad. Okay, so just clear everything on the screen. Okay. Okay, so let me go with another track. Okay. Okay, so let me check whether something is similar. Yeah, nothing is similar. So here what we can so what should here you do is you should find the expression for D4, D3, D2, D1. You need to find the expressions for D4, D3, D2, D1 and apply it in the counter. Okay. So how will you do that? That is the next question. Okay, that is the next question that is coming out. Okay. Now, if you are writing, what is D2? Yeah. Okay. So one way is you can redesign the counters such that you will get the expression for D4, D3, D2, and D1 separately. Now see, we can see that D1 nothing is there, right? All elements are 0. Whether there is any problem in that, please check. If it is 1, it will go to 0. So yeah, at least one of the elements should be equal to 1, right? So if it is 8, 4, if it is 2, should go to 1. Okay, so there is a mistake over here. So okay, I am just okay. So let me wait there. Let me cancel this out for the time. Okay. Okay, let me cancel this out. I will draw the present state next state table once more. There is a mistake over here. Okay. I will draw the present state next state table once more. Present state. One second. There is a mistake in the previous one, otherwise we cannot derive it. So let me check. That is I will draw a present state next state table. Present state next state. So you have Q4, Q3, Q2, Q1, Q4, Q3, Q2, Q1, D4, D3, D2, D1. So I will write start from 0. Okay, I can write all the 15. So it is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and 8. Is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 0, 0, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Okay. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Now if it is 0, it will go to 1, 0, 0, 0. If it is 1, it will go to 8. So 8, 4, 2, 1, so it will go to 8. So it is 1, 0, 0, 0. If it is 2, 8, 4, 2, it will go to 1. So it is 0, 0, 0, 1. If it is 3, 3 means it will go back to 8. That is 1, 0, 0, 0. If it is 4, it will go to 2. That is 0, 1, 0, 0, 1, 0. Yeah. If it is 5, it will go to 8. That is as per our discussion, we can make it into 8. If it is 6, it will go to 8. Okay. If it is 7, also it will go to 8. If it is 8, it will go to 4. That is 0, 1, 0, 0. If it is now all other states are invalid, so we can make it into 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. So if you are writing the decimal equivalence here, you will get of the present state 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. From 9 to 15, everything is invalid state, so you are going into 8. Okay. Now coming into D4, D3, D2, D1. So it is same as Q4, Q3, Q1, Q2, Q1. So you will get 1, 0, 0, 0. Again 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. Then 1, 0, 0, 0, 0, 0, 1, 0. Here you will get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay. Now again 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. We have done like this because D is equal to next state Q. That means D4 is equal to next state. That means D4, D3, D2 and D1 is equal to next state Q1, Q4, Q3, Q2, Q1. So that is from the characteristic equation of D. We have taken like that. Now, how we can take D1? D1 is only there for 2. Therefore, D1 is 1 is only there for 2. Therefore, we can write D1 is equal to Q4 bar, Q3 bar, Q2, Q1 bar. Q4 bar, Q3 bar, Q2, Q1 bar, Q2, Q1 bar. Now again coming to D2. D2 is only there for 4, right? Therefore we can write D2 is equal to Q4 bar, Q3, Q4 bar, Q3, right? Q4 bar, Q3, Q2 bar, Q1 bar, Q2 bar, Q1 bar. So that is D2. Now coming into D3. D3 is 1 only for this 8. So we can write D3 is equal to Q4, D3 is equal to, we can write it as Q4, Q3 bar, Q4, D3 we can write as Q4, Q3 bar, Q2 bar, Q1 bar, Q4, Q3 bar, Q2 bar, Q1 bar. Okay, so we have got the expression for D1, D2 and D3. Now coming into D4. Okay, if you are looking into D4, you need to derive the expression for D4 using K-map, using present state Q4, Q3, Q2, Q1. So coming into D4. Okay, that is the next question. So D4 you need to derive it D4 you need to derive it, right? Okay. So I am going for the K-map of D4. I am going to the K-map of D4. So you will get K-map of D4. You will get like this: 1, 2, 3, 1, 2, 3. So we get Q4, Q3, Q2, Q1. So this is 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 0, 0, 1, 1, 1, 1, 0. So here you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now coming into D4. Coming into D4. Where are you getting 1? For 0 and 1 it is 1. For 0 and 1 it is 1. Then for 2 it is 0, 3 it is 1. 2 is 0, 3 it is 1. Now coming into 4 it is 0, 5, 6 and 1. 4 it is 0, 5, 6 and 7 it is 1. Now coming into 8 it is 0 and all other elements are 1. For 8 it is 0 and all other elements it is 1. Okay. Now how to club these 4? That is how to club. That is a question that is coming in. Okay. So how to club? How to club? That is a question. So first I am clubbing. First I am going to club a quad. I have formed a quad here. Okay. So no, not quad. It is octet. So I have formed an octet. So what is common there? If you are forming an octet, it is common. You can check the column. So which is common? Only Q1 is common. So Q1 I am taking it as common. Now you can include this one. Next one is you need to include this one and this one. That is it, right? So you can have another quad. So you can have another quad like this. To include these two ones, you can have this quad, right? Yeah. Okay. If you are having that quad, what will you get? You will get Q4, Q3. That is Q4, Q3. Now coming in, now which is remaining? Now which is remaining is that this one is remaining, this one is remaining, and this one is remaining. So how to include that 3 ones? So you can have quads and pairs. That is it. So you can, if you are having one more quad, if you are taking this quad here, if you are taking a quad here, if you are taking a quad here, what will you get? Which is common? Q4 is common here, and here which one is common? Q2 is common. So we get Q4, Q2. Now how do you account for this 1? If you need to account for this 1, you can club these two. You can club this one and this one. That is how you can pair. So what is there? Which is common? Q4 bar Q3 is common. Q4 bar Q3 is common. And here which is common? Q2 is common. Q4 bar Q3 Q2. Now to include the first one in the 0th place, you can club, or you can club. So there we can club these two. You can club these two ones, right? So there what is the expression for that? That is here what is Q4 bar Q3 bar is common. Q4 bar Q3 bar is common, along with what is common? Q2 bar. Q2 bar is common. Therefore we can write D as D4 as D4 is equal to Q1 or Q4 Q3 or Q4 Q2. Yeah, Q1 is there, Q4 Q3 is there, Q4 Q2 is there. Then comes or Q4 bar Q3 U2 or Q4 bar Q3 U2, and last one or Q4 bar Q3 bar Q2 bar. Okay, so we got the for D4. Now let me draw the logic circuit. So you are having D4. Okay, so having D4, Q4, Q4 bar. Now coming into D3, that is Q3, Q3 bar. Now coming into D2, what you have is Q2 and Q2 bar. Now coming into D1, for D1 what you have is Q1 and Q1 bar. Okay, for D1 what you have is Q1 and Q1 bar, and clock is common to all these things. Clock is common. Clock is common. Clock is common. Now coming into D4. What is D4? Q1. Okay, I'll make it as an OR gate. Okay, that is Q1 to D4. So what do you get? Before Q1, then comes Q4, Q3. I am drawing a simplified circuit. Then comes what? Then comes Q4, Q2. Q4, Q2. Then comes Q4 bar, Q3, Q2. Q4 bar, Q3, Q2. Then the last element is Q4 bar, Q3 bar, Q2 bar. Last element you will get Q4 bar, Q3 bar, Q2 bar. That is D4. Now what is D3? D3 is Q4, Q3 bar, Q4, Q3 bar, Q2 bar, Q1 bar. So you can write D3 as Q4, Q3 bar, Q2 bar, Q1 bar. Okay, because I am not drawing the entire circuit. Now what is D2? D2 is Q4 bar, Q3, Q4 bar, Q3, Q2 bar, Q1 bar. Now what is D1? D1 is what is D1? D1 is Q4 bar, Q3 bar, Q4 bar, Q3 bar, Q2, Q1 bar. Here we can take Q4 is taken out, Q3 is taken out, Q2 is taken out, and Q1 is taken out. Okay, so this is how you can avoid lockout condition in this circuit. Okay, so that is how you can avoid lockout condition in ring counter. Okay, so how to avoid lockout condition in Johnson counter, that you can deal by yourself. Okay, so there are so many methods in which, so here I have shown only one method by redesigning the counter in such a way that by including the invalid states and making the invalid states into 8. By making all the invalid states then in one clock pulse is equal to 8. That is one method. Or another method is you can reset the entire counter when it comes into invalid states. There are another method is you can go with anything. You can make it to if invalid states encounters, you can make it to any of the valid states. But here I have made it to 8. This is one of the methods. Okay, and to get a self-starting Johnson counter, that you can do it by yourself. So that is all regarding shift register counters. Okay, so in this lecture we have dealt with shift register counters. What is ring counter? What is Johnson counter? This Johnson counter is also known as twisted ring counter. Then we have designed a twisted ring counter as well as a twisted ring counter based on D flip-flop, and we have drawn the logic circuit, and after that we have derived the logic circuit. Okay, so that is all from my part. Okay, and for this lecture, thank you.